Welcome everyone to reinforcement learning, and now we're gonna see what happens if I nudge my policy a little bit, whether we can improve our policy and win more often. Policy gradient methods are designed to find the optimal policy, pretty much like Q-learning as well, but Q-learning is a model-free method that is value-based. So we have no explicit representation of the policy, and if we want to find the optimal policy, we have to take a look at our estimates of the Q values and then take the policy for which the Q values are the highest. Policy gradient methods, in contrast, they do not work on the value function. In fact, there is no explicit representation of the value function, but they work on the policies directly, which makes sense because that's the goal, to find the optimal policy. They have in common that they're also model free, and of course in the background the value function is going to play a role. How this works, let's take a look at a stochastic policy, which we denote by pi, and parameterize this stochastic policy by theta. And this policy is a probability of taking an action A, and that could be discrete action. So we could say with probability 70% we take one action and 30% the other action in a given state. And the theta could be precisely already the probabilities that we use, but they could be also more complicated objects. Now, if we have these discrete actions and we want to use some gradient methods, one problem is that we need a smooth function to take the gradient. Now, this specification of a stochastic policy actually allows us to specify a smooth and continuous function for which it is easy to take the gradient. For these discrete actions, the softmax exploration is a commonly used specification, and it's also known as Boltzmann exploration. Now, in this specification, we have a numerical value that is given by a function of the state action pair and the parameter, and we put that into an exponential function so that it becomes positive. And we do that for all the actions. And so if we take the exponential function of this number for one action and divide it by the sum of the exponentials with the values of all the actions, then we normalize this to be between 0 and 1. And the exponential takes care that it's all a positive value. And so we have something that is also smooth and continuous, and we can take the gradient easily. Now, what we put inside could be actually a linear function. So, for example, this could be a base function f of the state action pair multiplied by the thetas, but it could be also a nonlinear function of the state action pairs and the parameters. So, in this case, we have managed to get a continuous function out of discrete actions, but we could also have continuous actions in the first place. Even then, it would make sense to specify a stochastic policy to find the optimal policy by changing our theta parameters a little bit. And so we specify here Gaussians for this continuous action A. And we have parameters here that are mu and sigma, which are the expected value and the covariance matrix that are dependent on the state and the parameters. So to see how we can actually now apply the policy gradient method, let's take a look at the stochastic gradient policy. And let's assume basically that we have a set of data where we get for each state an action that is optimal. So we know in this case by our oracle the label of the action. So we know that the action is optimal just by assumption. And so we have these state action pairs. Now, if we have this sample of state action pairs, we can actually use our model of the probability and write up a maximum likelihood problem where we maximize the likelihood to take the best action. Yeah? So by changing theta a little bit. And so how to solve this maximum likelihood problem is by taking the gradient with respect to theta. And if we do that, we get here the gradient with respect to theta of the log of the policy, the stochastic policy, the probability to take action A star, that is the best one given the state. Then we have a learning rate or step size alpha n, with which we update our parameter theta. Now, this is supervised learning because we know already which is the best action. In reinforcement learning, this is different. Here we don't know which action is the best in a given state, but what we have is a weak signal of how well this action performed. So we have state action reward triples and a set of them. So we have a sample of state action reward triples that we can use to also write up a maximum likelihood problem where we just want to maximize the sum of discounted expected rewards given the state action pair. And this is nothing else than the value function. So we want to maximize our value function by choosing the right theta. Now here the question is, how does the stochastic policy gradient update look like? We need to derive that. And so the answer is already here on this slide, but we were going to see that this derivation needs a little bit more thought. So what is the difference here to the supervised policy case? We can go back here. We see the gradient with respect to theta of this log policy is the same here. We also have a learning rate, and the updating works in the same way. The only difference is that we have gamma to the power of n times gn here as well. This is in addition. Now, what is gamma is the discount factor as usual. And what is gn? That's the Monte Carlo estimate of a trajectory of discounted future rewards. So it's just one episode of the future rewards that we sum up here and discount. Now, how to get this stochastic policy gradient update? To understand this, we must take a look at the stochastic gradient policy theorem, which states the following. It says that the gradient of the value function is proportional to the sum of over all states of mu, which is a stationary state distribution when we execute the policy parameterized by theta. So this mu is going to be difficult to obtain, so we need to give it also a little bit of thought how we can deal with it. Now, but if we have it, then we can multiply this. Basically, you can think of what is the probability to go do the transition from state S to another state X in the future. We multiply this with the sum over all actions times the gradient of the policy, which gives the direction in which we can improve actually the policy, times the Q value. And the Q value is the discounted sum of rewards when starting in state S and executing action A and then following the policy parameterized by theta thereafter. Now, to understand this a little bit better, let's take a look at the gradient of the value function. And we can rewrite this as the sum over all the actions and the product of the policy and the Q value here for each state. And now, if we take the gradient, we can use the product rule, so we get the gradient of the policy times the Q value plus the policy times the gradient of the Q value for all the actions. So we sum that up. And now if we look at this right-hand side here, we can actually rewrite the Q function as the sum of the probability to arrive in S prime and get reward R times the immediate reward R plus the discounted value of the state S prime. And so if you take the derivative here, the gradient here, then the theta does not appear here in this R, so the R drops out and we get this expression where we only have then the gradient of the value in the state S prime. And now if you look at this very closely, you see that this blue object here and the gradient of the value function is a recursive formulation, so we can unroll this problem, and this gives the next line here where we have just inserted what this gradient of the value function in the future state is going to be. And we can do this even further and then collect terms. Then we get a double sum here of a discounted probability, and then we have this sum over all the actions again times the gradient of the policy weighted by the future rewards. So this is familiar already. But what is this term here in the beginning? This is just so this probability is just the probability of transitioning from state S to state X in k steps under the policy pi. And then we do this for all the states and all the steps. And so if we have this result, we can move on and write it up again. So nothing changed here, but we want to take a look at this double sum here, which gives us the transition basically. And so this turns out to be proportional to the sum over all the states, and the mu, summing the mu's up over all the states. So that's basically the stationary distribution. And we just copy the right-hand side here. So we still have our gradient of the policy weighted by the Q function, and we sum that up over all the actions. Now, we have actually already here now the components of the stochastic gradient policy theorem. Now, to make this usable in practice, we need to do another couple of steps. So let's write this up, and we want to actually get rid of this sum here and the mu, and also the other sum here, because this is for all the states. We want to see what happens at the state that we are in. So we can just put here the state S and the current state that we are in, and then use the expectation instead of this sum. So we get this expression here. And in that expectation, we still have all possible actions that we can take, and that's again also very interesting. And we could solve actually this problem already now, but we want to see how we can actually use the actions that we actually have taken. And so to do that, we need to expand this expression by multiplying and dividing by the policy pi. And then we can actually simplify this to have here the actual action that we have taken. And then we have the gradient of the value function being equal to the expectation of the discounted future rewards times this gradient of the policy divided by the policy itself. So the interpretation is a little bit that this gradient here gives the direction, and this is positively related to the gradient of the value function, and the probability itself, actually, if we haven't used that policy, that means that we should use it more often in our update. So that's why it's inversely related to the gradient of the value function. And this is weighted by the discounted future rewards. Now we can write this fraction in more compact form. So we have here the log of pi, which is equal to this. And we can replace the Q with our Monte Carlo estimate here. And with this, we get the stochastic gradient at time step n, which is just this equation that we have seen already before. And now, as mentioned just now, the interpretation of this is that we have the discounted returns, which is this, times the direction that most increases the probability of repeating the action an on future visits of the state Sn. Now, with this, we can take a look at the reinforced algorithm. And the reinforced algorithm is one of the oldest reinforcement learning algorithm, and it is a Monte Carlo policy gradient algorithm. So how does it work? We initialize pi to anything, and then we loop forever. So we run several episodes and generate triples of state action rewards, and so on, for the policy pi theta. And then for each step in the episodes, we actually calculate the sum of the discounted rewards that are yet to come, and sum that up and put that into our policy update, and then we update and repeat this to find the optimal policy. Now, policy gradient methods are heavily used in practice still, even today, even if it's a quite old method. And so, for example, in the game of Go, where the rules are that you have two players, black and white, and they alternate with their turns, and each player places a stone on an intersection, and then tries to capture some areas. So in this game with a large state space, we can actually use these policy gradient methods. And actually, before policy gradient methods have been used, some reinforcement learning algorithms have tried to beat players, professional Go players, but with Monte Carlo tree search. But the success really happened when deep reinforcement learning has been using policy gradient methods, and AlphaGo actually could beat Fan Hui, one of the best players in Europe. And not only that, in March 2016, AlphaGo actually defeated Lee Sedol, who has done number 9, so a very professional player. And Kije, the world champion at the time, said, AlphaGo can't beat me. But just in May 2017, AlphaGo defeated Kije as well. And he said last year AlphaGo was still quite human-like when it played, but this year it became like a god of Go. So this shows the power of the policy gradient methods. And here are some references, and just to wrap up, policy gradient methods directly optimize behavior to maximize reward. And they explore actions using stochastic policies that are specified using a softmax or a Gaussian distribution. And good actions are reinforced by increasing their selection probability. And well, we have seen impressive demonstrations by AlphaGo combining different methods. Among those is policy gradient methods that we have just seen. Thanks for watching.